Today we'll be looking at limits of rational functions. I have an easy example to start off with, and then we're going to do a slightly harder example of the same basic nature. And then after that we're going to prove the quotient rule for limits. Okay? So let's begin by proving that the limit as x approaches 2 of 1 over x equals a half. Okay? Proof. Let epsilon greater than 0 be given, and let delta equal something. As usual, we're also going to let x satisfying 0 less than x minus 2 less than delta be given. And we're going to start our proof. So let's write in our function and our limit, 1 over x minus 1 over 2. And we need to mess around with this and conclude, hopefully, that this will be less than epsilon, using this information somewhere along the way. All right? So what is the first thing you think we should do here? Well, I see a fraction, I see another fraction. Let's subtract them. Common denominator and subtract. We're going to have what? 2 minus x over x times 2. Okay? Now the absolute value will split over the fraction. So we're going to put the absolute value on the top and on the bottom. So this is abs 2 minus x over abs x times 2. And we can clean that up a little bit. Switch the order here. Abs x minus 2 is abs 2 minus x is the same thing as abs x minus 2. And we can put the 2 in front here and then have the abs x in the denominator. Now, look at what we have. At the top, we have something which is bounded above by delta. In the bottom, we have a 2. That's all right. The abs x is not all right. We need to find an upper bound on this 1 over abs x quantity. Okay? So let's take a look at the graph. It's always helpful to visualize, if you can. In this case, we can. We know what 1 over x looks like. There it is right there. And we're looking at the point at 2. Okay? We need to get an upper bound on 1 over x. So what exactly do we need to do? Well, let's say this is our delta window. Okay? The upper bound on 1 over x, the largest that 1 over x can be, within this delta window around 2, would be this point over here. Okay? The furthest over to the left that we can go in our delta window. All right? Now notice that our delta window cannot extend past 0. It can't be bigger than 2, because otherwise we'll encompass the vertical asymptote, and 1 over x will be unbounded. If delta here is bigger than 2, 0 would be a possibility for x, and then we'd be dividing by 0 here, okay? Which is a big no-no. So what we have to do is make sure that delta is not bigger than 2. We don't want the asymptote included. So a good thing to do at this point would be to stipulate some maximum value for delta. Any value strictly less than 2 would work, okay? For instance, 1. Suppose that our delta window goes from 1 to 3, or is smaller than this window that goes from 1 to 3, okay? So at this point, I'm going to stipulate delta less than or equal to 1, all right? So what does that tell us? That tells us that x minus 2 is less than 1, or that x lives between 1 and 3. So if we want to expand out this absolute value, we have negative 1 less than x minus 2 less than 1, and now adding 2 to both sides gives us 1 less than x less than 3. So exactly what we see here from the graph. Okay? Now, what is the maximum that 1 over x can be? Well, should be 1, shouldn't it? The maximum that 1 over x can be would be 1. The minimum that 1 over x can be in that interval would be a third. Okay? Or we can get that from the inequality. We flip everything. So let's take reciprocals. And we do indeed get that 1 over x is less than 1 over 1. Okay? So the 1 over x quantity here, this absolute value of x in the bottom, can be replaced with a 1. All right? So let's continue over here. So this piece is strictly less than x minus 2 over 2 times 1. And now we're almost done. We're ready to bring in our delta. Delta comes in. 2 times 1 is 2. And now we're ready to set delta equal to, say, 2 epsilon. Okay? So which delta do we need? Well, we have to have delta less than or equal to 1. So we have a minimum coming in, 1 and 2 epsilon. Okay? It would also be correct, if you don't like the 2 epsilon, you would prefer just to have an epsilon. It would also be correct to remove the 2. There's nothing wrong with that. Why? Because delta over 2 is less than delta. And we can set delta equal to epsilon. So again, we can simplify things as much as possible to have the value for delta look as nice as it can. We want to remove constants if we can. Okay? So that's the end of that. Now, this approach of expanding out the absolute value is perhaps not the best approach. Here it's fine because we know something about the value that we're approaching. We know where 2 is. It's out over here. And within a window around 2, our x's will be positive. Okay? So it's fine to expand out the absolute value like this, but in a sec we're going to do an example where we prove that this function is continuous at every non-zero point a, and for that it'll be helpful to use the reverse triangle inequality instead of expanding up, because in that example we won't know whether a is positive or negative. We're going to try to do both cases at once. So instead of using this approach, a better way to do this would be to use reverse triangle inequality. So using reverse triangle, okay, which could also be written like this. What would we have? Well, we want to apply reverse triangle inequality to this. So we could write something like that. Notice we switched the order over here inside the absolute value, but that doesn't matter. The reason why we switched the order is because we need an upper bound on 1 over x. We need an upper bound on 1 over x, so we would like a lower bound on x. This will give us a lower bound on x because x now gets brought over, okay? And x will be greater than or equal to 2 minus 1. So if we now simplify this, we get 2 minus 1 is less than or equal to abs x. And therefore, 1 over abs x is less than or equal to 1. So this is the reverse triangle approach. This is the writing the absolute value in interval notation approach. And this is a better approach if you want to do things in general. Okay? This is probably a better approach since it's a bit more intuitive if you're working at a specific value of 2. Okay? So now we're going to prove that this function is continuous at all non-zero points, and you'll see the reverse triangle inequality in action. The proof will be very similar to this argument. Let's do it now. All right, so let's generalize the previous example. We're going to prove that 1 over x is continuous everywhere except at 0. Okay? So, same 3 lines and a very similar argument. 1 over x minus 1 over a. Let's simplify this. As before, this is equal to a minus x over x times a, if we get a common denominator, which is equal to abs x minus a over abs a abs x. Okay? The numerator is less than delta. The denominator has an abs a in it, which is absolutely okay. The only thing we need to worry about is the abs x in the denominator. Okay? That's what we need to bound. Now, what did we do last time? We needed to make sure that delta is not too large, because otherwise the x, which is living within the delta window centered around a, might stray too close to the asymptote, or perhaps even be equal to 0, and then we have a division problem. So we have to make sure that x can't be too close to the asymptote. How do we do that? Suppose that A is out here on the positive side of the real axis. Let us stipulate that delta is not bigger than A over 2. What would that mean? That would mean that our delta window can't be bigger than this, okay? And now x can't be closer to the asymptote than half the distance from A, all right? We didn't have to choose half the distance from A. A over 3 could have worked as well, or 2/3 A could have worked as well for a delta. But A over 2 works, so that's good enough, okay? So let us stipulate that delta is less than or equal to A over 2. Now, we do need the absolute value around the A. Why do we need that? Because A could be negative, right? A could be out here, and then we don't want delta to be smaller than halfway to the asymptote. So we would have to take our absolute value because we would need a positive distance here. We need to make that positive, okay? So delta would have to be less than or equal to abs A over 2. Now, if you feel uncomfortable doing both cases at once, we could prove that this function is continuous separately for all positive A's and for all negative A's. But we could also do both together. Okay? So we stipulate that delta is less than or equal to abs A over 2. And now what will that tell us about 1 over abs x? Well, A is here, then A over 2 is going to be over here. And the most that 1 over x can be is if you choose your x's very, very close to this edge. 1 over x then being mapped to 2 over A. Okay? Same thing on the other side. If our A is out here, okay, then A over 2 will be over here. Okay? This distance will be abs A over 2. And the maximum value of the function will be negative 2 over A. Or the maximum value of 1 over abs x will be 2 over abs A. All right? So we make that stipulation, and now we begin with our x minus A less than or equal to abs A over 2. Okay? And we figure out an upper bound on 1 over x. In order to get an upper bound on 1 over x, we need a lower bound on x, or on abs x. And for that, the reverse triangle inequality comes in. Okay? It's now harder to expand this and use interval notation. What would expanding look like? Well, we would have, first of all, that should be strict. Sorry about that. We would have this. And now we have a problem, because how does A add? And which side is bigger, right? You wouldn't know. You'd have to consider cases of positive and negative A separately. It's better to use reverse triangle inequality at this moment. Not expand out the absolute value, but to do the very same trick that we did last time, okay? We switched the order of that, and then we used reverse triangle inequality, and we had this situation. Abs A minus abs x is less than or equal to abs A minus x, which is equal to abs x minus A, which is less than abs A over 2. The abs A gets brought over, the x gets brought over. Abs A minus abs A over 2 is less than or equal to abs x, therefore. Which implies that abs A over 2 is less than or equal to abs x. We have a lower bound on abs x. That gives us an upper bound on 1 over abs x. Okay? So notice, regular triangle inequality is good for getting an upper bound on x. Reverse triangle inequality is good for getting a lower bound on x, which is an upper bound on 1 over x. Okay? Important. So this implies that 2 over abs A is greater than or equal to abs x. Or let's reverse that. 1 over abs x is less than or equal to 2 over abs A. All right? And now we can put that in our proof. So the abs x minus A at the top is less than delta. And then we can replace the abs x in the bottom with a 2 over abs A. Okay? Like that. All right? 1 over abs x gets replaced with 2 over abs A. There we go. And now what happens? Well, we have to choose the right delta, okay? The x's are now gone. We have a constant here times delta. What does delta have to be? Well, we have 2 over a squared. The absolute value can disappear because we now have abs a times abs a is abs a squared, which is the same thing as a squared. And what do we have to let our delta be? A squared over 2 times epsilon. So this business now cancels out, and we just get epsilon at the end. The proof is done, and delta has to be what? The minimum of abs a over 2. That's our initial stipulation. And a squared over 2 epsilon. Okay? Again, we didn't have to make this stipulation. We could have chosen a different quantity here. But no matter which quantity we chose, we would have to have it be less than abs a, strictly. Okay? So we could have selected abs a over 3 or abs a over 4 or anything else. You can try yourself with abs a over 3, see what changes in the proof. Okay? There'll be a 3 here, there'll be a 3 there. But other than that, the whole proof will be the same. So no real changes. But we cannot choose a constant value that doesn't depend on a. We can't choose 1, for example, because we'll get a problem if a happens to be closer to the asymptote than 1. Similarly, we get a problem if we chose any other constant, like a half or a third or a quarter. A might still be less than that. So the constant that we pick has to be in terms of a. We don't know what a is. We want to make sure that delta is not bigger than a. Okay? Now let's move on to the quotient rule. So now we're ready to prove the general quotient rule for limits. Okay? This proof will be a little more involved than the proof of the product rule and the sum rule last time, but I think we can do it. Since we've had 2 examples already, saw how to deal with quotients, and the general case is not that much harder. Okay? So I've written out everything we need to start the proof. Here's what the quotient rule for limits states, first of all. We're assuming that the limit as x approaches a of f of x exists and equals L. There are no restrictions on what L can be, or a. And we know that we're assuming that the limit as x approaches a of g of x exists and equals m. And here we need to suppose that m is not equal to 0. Okay? Since division by 0 is a problem. All right? Now the limit of the quotient could exist if the function in the denominator tends to 0, if f of x tends to 0 as well, but that's sort of a separate case. That's a much more subtle case. We won't touch that. Okay? We're going to assume that the limit of g of x is not equal to 0, and we're going to show that the quotient function, f over g of x, tends to the limit L over M. So this limit here exists and equals to that value. Okay? So what do we know? Well, we're assuming these 2 things, right? So like last time, it's good to start off with what you know. What we know is that for all epsilon, there's a delta 1, such that if x is within delta 1 around a, f of x minus L can be made less than epsilon. Now I didn't fill in what this expression will be, because if you remember the proof of the product rule last time, the expression could be some complicated constant times epsilon. So we're just going to leave that blank for now, and we'll fill in those expressions as we complete the proof. Okay? Same thing over here. We know there exists a delta 2 such that this implies this. This is just coming from the definition here. And we're going to fill in that expression. Now I left a blank line here. Again, if you remember back to the product rule, we did need to choose a delta 3. So we might need to do that again, and that's why that line is there. In fact, we will do it again. All right, let's actually start the proof now. Same 3 lines. And let's begin. F of x, f over g of x, the quotient function, minus L over m. Let's expand this out. This is f of x over g of x minus L over m. If we put things under a common denominator, we get f of x times m minus L times g of x in the numerator. And in the denominator, we're going to have g of x times L. Okay? The absolute value will split. It will go on the top and on the bottom. So we're going to have abs f of x times m minus L g of x over abs m abs g of x. Okay? Now, what must we do to the top? Well, we want to use this information that we have. At the moment, we can't split this up with triangle inequality or do anything in order to bring these quantities here that we know something about into the proof. Okay? So we're going to do a similar trick that we did with the product rule. We're going to add and subtract the same thing to the inside of that absolute value. Okay? Now, we want to have f of x minus L pop out, and hopefully g of x minus m as well. A good quantity to add and subtract would be the product of the limits L times m. Because if we, let's say, subtracted here L times m, then we see that an m factored out of those first two terms will give us f of x minus L in brackets. Similarly, adding back on the L times m and removing the L from the second two terms will give us m minus g, which is something we want. Okay? So let's do that. And again, how would you arrive at this by yourself? Well, it's just a trick. Add and subtract the same thing. It's a very common trick. If you don't know what to do with an absolute value, that's usually one of the first places you should look. And then it's just a matter of guessing the right thing to add and subtract. We could also, by the way, add and subtract f times g. But that makes things a little bit more complicated. Okay? So let's add and subtract L times m. So we have f of x times m minus L times m plus L times m, minus L times g of x. Close the abs. Over m abs and g in abs. All right? Now, we're ready to split this up using triangle inequality and factor out an m from here and an L from here. Let's do that all in one step. We're going to do it here, since we're going to need the room. Less than or equal to abs m times abs f of x minus L plus abs L abs g of x minus m over abs m abs g of x. All right, now this is looking good. If we choose that quantity to be epsilon over abs m, and this quantity here to be less than epsilon over abs L, then these two quantities can be made less than epsilon plus epsilon. Okay? So that's progress. We can totally do that. It won't quite work because we have a denominator to get rid of. All right? Now, the m in the denominator is okay. The g in the denominator is not okay. As before, where we had an abs x in the denominator, we need to find a bound on this 1 over abs g. Okay? So at this point, I'm going to continue up here on this half. We need to bound 1 over g of x in abs values. Okay? We want to find an upper bound on this. We want to say that this is less than something. So, how are we going to do this? Well, let's visualize, as we did before with our 1 over x example. Okay? Let's draw a function g. Now, we don't know what g looks like, but let's just draw the random looking function. And let's label a. Let's say a is over here. Okay? So m in this case will be up here. Right? A could have been over here, then m would have been negative. That would be fine as well, as long as a is not a root of g of x, because then the limit would be 0. Okay? So let's assume we have this situation. We need to find an upper bound on 1 over abs g of x. What does that mean? We need to find a lower bound on abs g of x, and then take reciprocals. So we need to find the smallest that abs g of x can be. Now, if we look at x's within a delta window around a, we can't have delta big enough that one of those x's could be a 0 of g. Okay? So we want to cut things off before a root comes in. The best way to do this is to use this second line here. Okay? we know that the limit as x approaches a of g of x exists and is non-zero. So we know that there exists a delta 2 such that this implication here holds. And now as long as this quantity is not bigger than m, we're okay. So we could choose an epsilon, or we could set epsilon equal to something like abs m over 2, and then we know from this line that there exists a delta 3, a different delta, which makes that happen. Okay? So what do we know? There exists a delta 3 greater than 0, such that 0 less than x minus a less than this delta 3 implies g of x minus m is less than abs m over 2. Okay? So on the graph, what that means is that there exists a little window delta 3, okay, around a, such that everything, all the x's within this little delta window around a, if we feed them into g, okay, the values, the outputs of g, are going to be in an interval, in an epsilon interval, size m over 2 around m. In this case, we have a positive. If m was negative, that would be a positive distance. In this case, we have an m over 2 window around m. Okay? So that's important. There's a little delta 3 here, such that no matter what we feed into our g, all the outputs lie within m over 2 around m. So in particular, the smallest that g of x could possibly be is m over 2. And it can't be 0. Okay? The smallest that g of x can be will be m over 2, meaning the largest that 1 over g of x can be will be 2 over m. Now, if the m happens to be negative, then we will need the abs value. Let's do this algebraically now. Okay? We're going to use the reverse triangle inequality like last time. All right? So, just like last time, we're going to begin with our abs m minus abs g of x. And we're going to apply the reverse triangle inequality. This is abs m minus g of x, which is equal to abs g of x minus m, as we know, which is less than abs m over 2 as long as x comes from the delta 3 window around a. So as long as our delta is less than or equal to this delta 3, which we know exists. As long as our delta is less than or equal to delta 3. This is now our stipulation. Okay? So just like last time, we stipulated a maximum value for delta. The difference with the 1 over x proof is that we could get that delta value explicitly. We stipulated delta to be less than or equal to abs a over 2, if you remember. In this case, since we're dealing with a general function g, we don't know how close a is to a root of g, or how quickly g will dip to make a root. All we can say is that there exists a delta 3, which makes this situation happen. And we don't really know what delta 3 is in terms of a, because we don't know g. But we don't need to know that. All we need to know is that there exists a little delta 3, which makes this work. And as long as our delta, the one we're going to use in the proof, is less than or equal to that new delta 3, we're good. The max value for 1 over g of x will be abs m over 2. Or abs 2 over m, rather. So we might as well add that delta 3 right in there. Okay? And what do we know? Well, looking at the reverse triangle inequality here, bring that part over, bring this part over. Reverse triangle inequality implies that abs m minus abs m over 2 is less than or equal to abs g of x. This part is abs m over 2. And now taking reciprocals of everything, that implies that 1 over abs g of x is less than 2 over abs m. Actually, that should be a strict inequality right there. Okay? So there we go. There's our upper bound on 1 over abs g of x, algebraically derived. Okay? 2 over abs m. Now, we're going to use that right there to get rid of the abs g of x in the bottom. But before we do that, we're going to replace these two quantities with something. Okay? If you remember back to the product rule proof, what we did is, in order to cancel out some constant in front of a g of x minus m or an f of x minus l, we needed to replace the abs value of our limit with 1 plus the abs value of the limit. We needed to make that inequality so that then, when we pick out our epsilon here, our epsilon value, which will be, in this case, epsilon over 2 times this limit value here, so that these cancel out, we want to avoid our division by 0. Now, L could be 0, so we have to definitely do that, add 1 over here to the L quantity. We don't have to do it to m, because we know that m is not equal to 0 anyway. But we can do it anyway for symmetry. It'll look a bit nicer. So let's do that. Why not, right? So this is going to be strictly less than 1 plus abs m, in brackets, f of x minus l, plus 1 plus abs l, g of x minus l, m, all divided by abs m. And now 1 over g of x, as we saw, was less than 2 over abs m. So we're going to replace the 1 over g of x with 2 over abs m. Now we can multiply this through and split this fraction apart. And what do we get? 2, 1 plus abs m over abs m squared, f of x minus l, plus 2 times 1 plus abs l over abs m squared g of x minus l. All right? Notice the symmetry here. That looks very similar to that. It's just that we have an abs m here and we have an abs l there. If we didn't add that 1, we would have a 2 abs m over abs m squared. The abs m's would cancel out. We'd have a 2 over abs m here and a much more complicated expression there. I don't know about you, but I find this a little more pleasing, that these two quantities look so similar. Okay? That's why I added that 1 there, even though it wasn't really necessary. Okay? The last step in our proof is we need to choose the right values for epsilon, such that this piece is going to be less than epsilon over 2, and that piece is going to be less than epsilon over 2. So that means that f of x minus l here, okay, we need a delta 1 such that f of x minus l can be made less than epsilon over 2 times all of this. So let's erase the graph and put in those values for epsilon. F of x minus l has to be made less than epsilon over 2 times all of this. So 2 times 1 plus abs m over abs m squared. And similarly here, I'm running out of room. There we go. Epsilon over 2 times 2, 1 plus abs l over abs m squared. And we can simplify this slightly. We can make that a 4, bring the abs m to the top, similarly here. Okay? And now, let's get rid of this. Each piece here, when we substitute this value in, will be less than epsilon over 2. And our final result is going to be epsilon. Okay? And finally, what does the delta need to be? Well, we have one piece that we need here, delta 3. Okay? And we also need the delta 1 and the delta 2 to make these statements true. So we're going to add in delta 1 and delta 2. There we go. So the delta has to be the minimum of these 3 deltas, and the proof follows. We used some algebra and all 3 of these given pieces of information. Okay, so thanks to the quotient rule, we can now conclude that all rational functions are continuous on their domains. If you remember what a rational function is, f of x is a rational function if it can be written as a ratio of 2 polynomial functions, p of x over q of x. And these 2 are polynomials of any degree. Okay? We can conclude that the limit as x approaches a of f of x equals the limit as x approaches a p of x over q of x, which is the limit as x approaches a p of x over the limit as x approaches a q of x, which equals p of a over Q of A, okay? Which is f of A. Okay? So the quotient rule, which we used over here to split up the limit, helps us in proving that all rational functions are continuous as long as the value A chosen is within the domain of the rational function, meaning Q of X, this limit, okay, Q of A is not equal to 0. Okay? So if you remember last time, we proved that all polynomial functions are continuous using the sum and product rules. That part we used here. Now we know that any rational function, any fraction of polynomial over polynomial is also continuous, as long as we don't approach a 0 of the denominator, so an asymptote of the function. Okay? So this actually proves a very large class of functions are continuous on their domains. Okay? So from the quotient rule, we know that things that look like this, 1 over x, 1 over, say, 1 plus x squared, 2x cubed minus 3x squared plus 1 over x to the 19 plus 5 is continuous on its domain. Any rational function you can think of is continuous. All we need to do is invoke the quotient rule, and we'd have proved that. Okay. Thanks for watching.